We are building the bit by bit project from the YByte Python curriculum available at www.ybyte.in. We have been looking at bitwise and or and XOR. These work with binary representations of the numbers that we're feeding in. In this video, we look at some very interesting special cases. Specifically, we look at what happens to any given number x, which is say an 8-bit number. It could be any number. What happens when I, let's say, do an AND with 255 or AND or an XOR, say, with 255 and also with, say, zeros. This slide, in fact, summarizes the whole picture. If I do an AND of a number with 255, in fact, I get back the same number. But if I do an AND with a 0, I get a 0. For OR, if I do an OR with 255, I will get a 255 at the end. If I do an OR with a 0, I'll still get a 255. So number will remain unchanged because, when I do an OR with a 0. If I do an XOR with the 255, in fact, the value of this number would be 255 minus X. And probably this is somewhat surprising, but we will see why this works out. And if I do an XOR of any number with a 0, the value will be X. Now, how do we understand this? How does this actually work? And why is this significant? Let's see it in a step-by-step manner. Now, in order to understand these special cases, let's say vividly, we will go back to the basics. We'll go back to the truth tables of the basic, let's say, AND or and XOR functions that we have seen before. Specifically, we look at it from a slightly different point of view. We'll ask ourselves a question that, look, if my input is, let's say, A, which is, say, 0 or 1, what happens if I fix my B to, say, 0 and, say, B to 1? So let's read that way. When I have any input A, it could be 0, it could be 1. If my B is 1, you notice that the output is the same as A. And that's just a reflection of the fact that, well, look, in an AND gate, the moment I have a single 0, output will be 0. So in this case, if my B is 1, my output is unchanged. If it's 0, it remains 0. If it's 1, it remains 1, which means that the output is same as the bit A. On the other hand, if I were to do an AND with a 0, which means I look at, let's say, row number 1 and row number 3, no matter what I have on the, let's say, bit A, 0 or 1, I will end up with a 0. In fact, this one observation explains that, look, when I do an AND with all zeros, I will end up with a 0. Let's see it more carefully. So I have any number. Remember, when I do a bitwise operation, the number gets converted to its binary representation. So it could be anything now, B7 until B0. It could be a combination of zeros and ones. But I am doing an AND with a 0, which means I am doing an AND with all zeros. No matter what I have got on these bit values, in fact, the result will be a 0. And which is why when I take zeros and AND with, let's say, any number, I will end up with a 0. On the other hand, when I do an AND with, let's say, 255, remember 255 is all ones. All I'm doing is that on every bit, I'm doing an AND with a 1. And remember, when I do an AND with a 1 for a single bit, that bit remains unchanged, which is why the output remains completely unchanged. Now, we can actually, in practical scenarios, we can do a combination of this, which means that we can say, okay, look, I'm going to do a AND with, say, 4 zeros followed by 4 ones. This is interesting. In fact, we'll see this in action because the output will have 4 zeros forced by, let's say, these 4 zeros and these 4 bits completely intact. In fact, so let's say, in fact, I can generalize this. If I want to say, for example, if I want to find out, let's say, the values of B5 and B4, again, could be 0, 1, could be anything. All I need to do is to do an AND with a mask. So 0, 0, 1, 1, 0, 0, 0, 0, because the output then will be 0, 0, B5 and 0, 0, 0, 0. So it's kind of like acting like a mask, and we will see this in action later on. Moving on to the OR gate. Once again, let's look at what's happening when I do an OR, let's say, with a 0 and then OR with a 1. So if I look at 0, ORing with a 0, so A is 0, the output is 0. If A is 1, the output is 1. Again, a reflection of the fact that any one input becoming 1 causes the output to be, let's say, 1. The consequence hence is that ORing with a 0 leaves the bit unchanged. Now see the contrast here. ANDing with a 0 leaves the bit 0, makes the bit 0. ORing with a 0 leaves the bit unchanged. On the other hand, when I OR with the 1, no matter whether I am 0 or 1, that's row number 2 and row number 4, let's say, I will end up with the 1, which means if I OR with the 1, I'll always end up with the 1. Extend this argument and we have our results. When I OR something, when I OR something with say 255 bitwise OR, remember I'm doing a bit by bit OR with all ones, which means that I will end up with all ones at the output, because the moment I have a 1 over here, doesn't matter if this is 0 or 1, I will end up with a 1, and hence the answer would be 255. So which means that ORing any number with 255 will result in a 255. On the other hand, if I were to do an OR, let's say any number with zeros, well, basically I will end up ORing every bit with a 0. I will leave every bit unchanged, and hence the output will remain same as the input. Again, we will use these facts to, sort of build our LED activity. Let's, however, look at the XOR. Now, in case of XOR, it's quite interesting. Again, let's think of the scenario where A is a 0 or 1. And what happens to A when I look at B being 0, B being 1? So let's look at row number 0 and, sorry, row number 1 and row number 3. In this case, A is 0, C is 0. A is 1, C is 1, which means that if I XOR a bit with a 0, in fact, it remains unchanged. Think through this, very, very interesting. Just a consequence of the fact that, look, both the outputs have to be, let's say, unequal for me to get a 1. So which means that if I XOR with a 0, I will end up with the bit being unchanged. But if I XOR with a 1, notice if in row number 2 and row number 4, bit B is 1. If I XOR is the 1, I will end up inverting the bit. Notice 0 becomes 1 and 1 becomes 0. Very, very, very interesting. Now, let's extend this argument. Bitwise XOR with all zeros. What does that mean? Well, I am doing an XOR of every bit with a 0. Remember, XOR with a 0 leaves a bit unchanged, because if it is 0 over here, well, 0, 0 will anyway be a 0. If it's a 1 over here, it will become 1 XOR 0, and that will remain 1. So this bit will be unchanged. From the truth table, we saw that, and hence the number will remain unchanged. But the moment I do an XOR with 255, something very interesting happens. Basically, I have got, let's say, B7 XOR with 1, B6 XOR with 1, and so on and so forth. Just look at both the cases. Let's say B7 is 0. 0 XOR 1 is a 1, which means that this bit here will be inverted. If B7 was 1, 1 XOR 1 is a 0. So in all scenarios, basically every bit will get inverted. Now, how do I know this is 255 minus the number? Well, that goes back to the binary representation. In fact, we can see this in action. So if I were to do, let's say, so I do, let's say 41, say 42 XOR with say 255. Well, in fact, I get 213. That's because 255 minus 42 is in fact 213. To see this a little bit more clearly, we can basically look at the binary value for 42. That is, say, 00101010. Whereas if I were to look at binary value for say 213, that is exactly reverse. So notice I got a 1 1. So I had a 0 0 here. I don't see it. 1 1 0 1 0 1 0 1. You notice that all the bits have been inverted, and basically what that results in is 255 minus this number. Now I'm not getting into the mathematics here, but happy to discuss if you have any questions on this. But this result is interesting. This result is important. We will in fact use this very fact, the fact that we can XOR with a 1 and invert, in our LED pattern. So for example, we will XOR, let's say, an entire pattern with, let's say, all ones, and you will see that toggling effect coming in. Like I said, seeing all of this will make it that much more illustrative, that much more vivid. But it's important for us to approach this in a step-by-step manner so that the picture becomes clear. I hope this has given you an idea of where we are going, and I hope this has been interesting. As always, think through this carefully. This is a little bit not so obvious because we are generally not used to these binary numbers. But with practice, with a bit of thought, with, let's say, thinking through examples, with playing with taking examples, things become a lot clearer. And of course, when we build the activity, it will be a lot more clearer. On that note, let me urge you to look at our website www.ybyte.in, because at Ybyte we learn Python in a very systematic step-by-step manner, connecting different facts to each other and resulting in activities that are fun to build. Take care. Thank you so much. Bye bye.